Okay. Okay. Works. Okay. Might as well start. Might as well start. Okay. Okay. People here? I don't know. Let's see. Hey. One person's here. Second person's here. The bot is here. Stream Elements bot. Okay. Oh, let's put the garbage music on. Background. Where's the garbage music? Why do I have to install Spotify? All right. Okay. Good. Okay, so let's just get some administrative things out of the way first. I'm also having Discord up so I can see if anyone says anything on Discord. Now, speaking of Discord. Okay, awesome, AC. Yeah. Okay, awesome. Awesome like a log. Got it. Okay. Speaking of Discord, go to the general channel and there is a straw poll that's asking whether the class wants to continue on Twitch or whether it wants to go to Zoom. More private, cozy setting, which I suspected would be a preference for grad students. So go and take that poll. Right now, let me click it. It's up. It's in the general channel. Got a nice yellow picture of some sort. Let me look at the results so far. It's 2-2. And there are 9 people that are relevant. So, you know, we got a Supreme Court situation here where 5 people are not showing up for work. Okay. So go and decide that. And then the class will change depending on the result. Okay? Good. So we should do that by Monday so that I know how to do Monday. Okay, good. No, don't tell me who voted. Don't tell me who voted which way. It doesn't matter. Just, I need to see 9 votes before I can say it's over. Good. So go do the straw poll. Next. Where are we in the book? First, like 6-7 pages. Ian McDonald. Okay? Great. Let me now start the class. You'll just be sad? Yeah, you'll just be sad. That's right. Pale blue. Okay. Ideals, primes, maximal ideals, and nil radicals. That's what we're going to cover today. Lots of stuff is review here. So, but let's go through it so we know our language going forward in the class. Okay. So I like to keep three parts because that's my pace, it seems, on online education. The first part is just going to be a bunch of definitions and conventions. Then primes, maximal ideals, and local rings. That's what this symbol means. A, M's. Local rings. just the definitions. And then the first part where there's a theorem of interest is right here. So this is the only real content that's outside of definitions. Definitions have content because you have to understand the damn thing. But this is the part that has a theorem. And it's a Zorn trick. So that's great. Okay, basic definitions, let's go. You should know what an ideal is, but okay, ring, without the usual ring we're gonna consider is A. That's a symbol for a ring. A and B and C's. That's what the book uses, so we'll keep it. Okay, now, if you have an ideal, you get a quotient map. You get a quotient ring and a quotient map. Send an element to the coset, to its coset. Good. It's a unique looking M. It's a fractor M, all right? Don't make fun of me, Will. Hey Kappa, how's it going? Quotient map. Q. All right? Should know what that is, of course. What's the most important thing that is used all the time in the context of this quotient? It is that what are ideals of the original ring versus ideals in the quotient? All right? Okay. So, most very frequently used easy. If this is new to you, do it as an exercise. Okay? All right. It's a very unique. Okay. Good joke. Good joke, Will. Should we pause and read the joke, or are you done, Will? Should I close the music for awkward silence? Okay, let's continue. Let's look at the fact. The fact is, the set of ideals containing ideals in the original ring containing A, the natural bijection with the ideals of the quotient ring. And the bijection is given by pre-image ideal. So if you have an ideal in here, you send that to the pre-image of that ideal. It's again an ideal in the upstairs ring, and it's an ideal that contains A. And every ideal that contains A arises this way by taking the image set, and then you have to prove that. Okay? That's the thing. All right? Now these are fractor. Fractor. Forget it, Kappa. All right, got it? So we could try to draw a picture of the situation, and we'll use that fact all the time. Transporting ideals from the quotient, what they mean in terms of the original ring. Okay. Great. Okay, let's move on to other convention type things. So rings always have ones. Okay, and if you have an element, if F is an element of a ring, then parentheses means ideal generated by, principal ideal generated by that element. And if you have, this is principal ideal generated by. That's what the parentheses will mean. And if you have several elements, then parentheses just means ideal generated by. I don't want that. That's it. That's the convention. Okay, good. And so when you see this, that just means the whole ring. Of course, right? Next, what's a unit? You should know what that is. A unit in a ring is a unit. A zero divisor. You should know what that is. A zero divisor is a zero divisor. Great. Okay. What else? What other definition, convention-y things should we recall? You should know what a field is. And here's something that should be easy for you to prove. Fields. Fields are the best kinds of rings from the ideal theoretic perspective, because here's a equivalence that you might want to try proving. You have a field. The only ideals are the zero ideal and the whole ring. Not zero or the whole ring. That's the only ideals. That's also equivalent to being a field. So this is the following are equivalent. All right. Here's another one. That anytime you see a homomorphism from A to anywhere, it's injective. Book uses the word monomorphism for injective. Stupid, but whatever. Don't tell me how you voted. It's fine. But everybody should just vote so I know what the consensus is by Monday. Okay, good. Got it? So these things are easy to. This is easy to establish, but you should know what a field is going into here. And fields are the best kinds of rings because from the ideal perspective, nothing interesting happening when it comes to ideals in a field. Okay, next definition. Prime ideal. Okay, let's move on to some more definitions. What does it mean for an ideal to be prime? An ideal, typically, you use a P. Is prime if whenever x times y is in P, either x is in P or y is in P. Okay, this is review. Right. Good question, Kappa. Good question. Is the map from a ring A to the ring wrong, the zero ring, is that a homomorphism? No. Good question. Convention. Homomorphisms take the element 1 to the element 1. So convention is homomorphism means the element 1 has to go to element 1 in the other ring. 1 goes to 1. Wait, that's fine. Hold on. Okay. Wait, hold on. That's funny. Hold on. That means there's still a map to the zero wrong. The zero wrong. Yeah, I know. Good question. Good questions, Kappa. Good. Yes. So, every homomorphism out of A to a non-zero ring. Every homomorphism out of A to a non-zero ring is injective. Okay. I wonder if does the book consider the zero ring as a ring? We'll have to look that up. Someone can look it up. All right. Good. Hey, root guy, thank you. Not necessary, but thank you. Yeah, forget the zero ring for most of all of this. All right, zero ring is stupid. Okay, this is prime if whenever product of two things is in the prime, this thing. Another way to say this, just to show you, is if you look at the complement. Oh, and this has to be a proper ideal. Not the whole ring. The whole ring does not count as a prime ideal. Okay, so another way to say this is that the complement of the prime ideal is closed under multiplication and contains the element 1. That's where the properness. Okay, so prime ideals are not the whole ring. Whole ring is not a prime. They don't exclude the zero ring. Okay, then can you look at AC? Can you take a look at this equivalence of or any one of the three things and see if they got rid of the non-zero ring part? Yeah. Okay. All right, good. I don't know where it is. It's somewhere in the first 5 pages. You'll see it. A is a field. A is ideals in A are 0 and 1. Every homomorphisms out of it is injective. Yeah, the following are equivalent. Yeah. You'll see it. You'll know it when you see it. And see if they have this thing. They messed up? Okay. Yeah. But not really, okay? Who cares about the zero ring? This is not a philosophy class. Okay, we're going to talk about real things here. All right, next. Okay, so just remember this. The complement of the prime ideal is closed under multiplication. Okay, good. Maximal ideals. We know what that is from last class. Awesome. So that's some definitions. Now, classic things you should already know. P is a prime if and only if A mod P is an integral domain. Okay. M is a maximal ideal if and only if A mod M is a field. Now, you can use this following is equivalent to get to the second criterion if you really want to do, or you can just do it by hand easily. Okay, unraveling definitions. Yes, the definition of a field excludes the zero ring. But I think in there, so in this case, the problem is, I don't know if in the proposition they excluded that the target ring of the homomorphism could be a zero ring or not. But forget the zero ring. Okay, good. Don't forget the zero ring. It's important for computer programs, I guess. But yeah. Yeah, exactly. Exactly. They didn't mess up? They allowed the ICO, did they say assume A is not the zero ring from the beginning of the proposition? Oh, okay. So they didn't phrase it like me. So this is my stupid way of phrasing. This is my bad. The first sentence is assume A is not the stupid zero ring. Then these are equivalent. Assume A is not zero. Okay, good. Good. Great. So we have these basic things that we know from previous algebra classes. Okay. Okay. So a lot of algebraic geometry and commutative algebra facts will be concerned with basically the study of prime ideals in a given ring. What does that mean? It's kind of like, what properties do all the ideals in a given ring have, vaguely? And in particular, what properties do the prime ideals have? Now, why are the prime ideals singled out among all ideals? I tried to explain one context in which the prime ideals show up very naturally in a document that I hand wrote and put in the dictionary channel. So go ahead and see one place where you can see why prime ideals are more natural to study than arbitrary ideals. Of course, prime numbers are a slightly more natural subset of numbers to study than arbitrary numbers, thanks to some fundamental theorem of algebra. And so it's some combination of these kinds of ideas that really narrows our focus to prime ideals. Okay, why are maximal ideals interesting? Well, I don't know, but maximal ideals get you from rings, arbitrary rings, to fields very quickly by a quotient map. So maximal ideals arise naturally when you're scared of random rings and you want to take a random ring and produce a field where you're very secure and safe, because everything's easy for fields. Okay, so bullshit explanation for first explanation at why primes and maximal ideals more important. Awesome. We'll try to make that. We'll try to grow our appreciation of them as we go. Next, what kind of other boring things? Good. Here are some corollaries of last time's Zorn's lemma statement. So last time, non-zero rings have maximal ideals. Zorn's lemma type trick. Okay, here's some quick consequences of that. Consequences. If you start with a proper ideal of a ring, then there is a maximal ideal that contains it. Okay? So you can upgrade a random ideal to a maximal ideal containing it. That is a true fact, as long as the ideal is not the whole ring. How does this follow from the previous? Because you apply the previous Zorn's lemma fact that every ring has a maximal ideal to A mod A. A mod A. This is going to be bad. Okay, apply last time to this and use the thing we constantly use. Use the dictionary between ideals in the quotient and ideals in the original ring. Okay, so you get that. Similarly, if you have any element that's not a unit, then it's contained in some maximal ideal. I'll look at chat in a second. Okay, this is just using the first Zorn's lemma fact with A mod the principal ideal F. Let me look at chat. Yes, yes, yes. Good. That's correct. Okay. Great, great. Okay, so every element is sitting in some maximal ideal, unless the element is, for many purposes, silly. Units are not to be worried. Units are friendly. You know, you multiplied by a unit, no problem. You can undo that. Other elements have real content. When you multiply by them, you lose. You lose information. You can't come back necessarily. Okay? So if as long as you have a real, a real element, a meaty one, it's contained in some maximal ideal. Awesome. Okay, great. So that's some basic facts about when to upgrade an ideal to a maximal ideal. Okay, so next we have a definition that involves maximal ideals. So we have a definition. The concept of a local ring. Okay, a ring is local if it has exactly one maximal ideal. Okay, so it's interesting. You should immediately ask, why are they using the phrase local for this concept? These are the beginning hints that the people who started this whole thing had geometry in their minds. Very geometric motivations. Okay? So there's a definition of a ring being a local ring if it has only one maximal ideal. We will see slowly why the word local makes sense once we add some geometric pictures and so on to this content. Okay, so but you should ask right now, why is it called local? All right, when you have a local ring, there's notation. Typically, M is the name of the maximal ideal in that ring. It's not saying that it has only one prime ideal. There could be prime ideals in A as well, but they're all contained inside of M. Everything's happening in M, okay? All the interesting ideals. So this is the notation that we usually use. The ring, comma, the name of the maximal ideal. That's the ideal generated by A and M. Oh, terrible. Good. Okay, good. I don't know what to do about this. All right. Would 0 be its maximal ideal then? Okay, a field, this is very confusing. A field is a local ring. However, there will be a concept for some of you called a local field. That's different. That's an abuse of that is unfortunately, it's unfortunate. It's unfortunate. All fields are local rings, okay? But there's another concept called a local field. That's a discussion for later, some other time. It's an abuse of the word, unfortunately. Okay, good. So here's how you write local rings. And every local ring has a particular field attached to it, namely the quotient by that ideal, by the maximal ideal. This is called the residue field. Okay, it's typically denoted by a little k, some flavor of a k, little k usually. Okay, great. Local rings. Local rings are nice because if you're trying to list all the ideals in a ring, you can try by starting with the largest ones, the maximal ideals, and you're going to get a nice list. And then you can try to order them by how big they are. I don't know. We'll understand a method for doing that eventually. Something called dimension. But you can start with the top, maximal ideals. Local rings are the easiest to start with. There's only one maximal ideal. That's why we like them. Okay, wonderful. That's the first reason. Good. Now, there are ways of knowing whether you're in a local ring. Ways of knowing that you're in a local ring. Okay? The most famous one is you're in a local ring if there's a kind of like a either you're a unit or you're in an ideal, a particular ideal. Okay? So you're in a local ring if there's some ideal for which everything outside of it's a unit, everything inside of it has content. Okay? So suppose A is a ring, and actually I'm gonna write the letter M for this thing, but an M is an ideal such that everything in the ring is either inside of the ideal or a unit. So how do you say that? So every element outside the ideal is invertible. Units or interesting? Dichotomy. If you're in such a ring, then that's a local ring. So part of the content is that that ideal has to be maximal, and it's the only maximal ideal in existence. All right, great. 27 lines. I'll show you the 27 lines in a second here. All right. So how do you proof is actually very simple of this thing, because first show that it's a maximal ideal. I'll just sketch it. How do you show that? Take an ideal that's bigger than M. It's going to have an element outside of M in it. You know, any ideal bigger contains an element that's not in M. But then that element's a unit, and so the number 1 is in the ideal. Ideal explodes. This is going to happen a lot. Like, you know, ideal will explode. Okay, we'll just call it ideal explodes. All right, so that's why this thing is a maximal ideal. Such a thing. And now, why is it the only maximal ideal? Because every interesting ideal, every proper ideal, is contained in some maximal ideal. So it has to be sorry, no. Okay. Sorry, why is it the only maximal ideal? Same argument. Take any ideal. If it has an element that's not in M, you can explode the ideal. Same argument. Done. Okay, we're done with this. But the point is, you know you're in a local ring if there's like an inside ideal and everything outside is unit. That's the feeling of a local ring. Okay. There's not a unique prime ideal necessarily, just a unique maximal ideal. Okay, great. That's as much as I want to say about local rings for now. They'll be used all the time as we go. It's a passing from a ring to a local ring is a version of simplifying a situation. Simplifying in the sense of, let's just start treating elements as either interesting or units. That's the flavor of simplification that passage to a local ring does or buys. Okay. What are some examples? Let's spend time on that now then. What are some examples of non-field local rings? Here's an example. Sajanin. Okay, so here's an example. I had some examples here prepared. Look at the fractions. Look at the fractions where 3 does not divide the denominator. Okay, this is some ring. This ring has a name. It's called Z parentheses 3. This is the name of this. Okay, this is a local ring. So you should try to establish that. The maximal ideal is things with numerator multiple of 3. Here's that's an example. All right. There's all kinds of different flavored local rings. There's this kind. There's here's another one, a geometric one. I will use the phrase geometric whenever you're constructing a ring by taking a polynomial ring and modding out by various equations. This is a local ring. Go and test it out. Okay. Here's an example. The power series ring. In X, that's a local ring. See if you can establish that. You have to sort of guess what the maximal ideal is in each of these, and then show that everything outside of it is a unit. All right, wonderful. Okay, so there are some interesting examples to think about. All right. Also, this is also this. There's only one maximal ideal. Great. Okay. There's double brackets there, not single brackets. Okay, non-examples. Z, C. Okay, lots of non-examples. Most things are not local rings. Local rings are great. Okay, how much time do I have? I have 8 minutes. Let's do some content. Ready? Okay, so the prime ideals are related to the concept of nilpotence. So definition, an element in a ring, an element F in a ring A is nilpotent if some power equals 0. Okay, you raise it to some power, it suddenly becomes 0. Very strange type of arithmetic. Okay, now as you know probably from from algebra, if you look at the collection of all nilpotent elements, that actually forms an ideal. It's called the NIL radical. I'm going to use the word NIL radical. Some people will just use the word radical. The problem is there's another radical that I don't understand as well geometrically called the Jacobson radical. It's going to show up just on the next page as we go here. All right, so the NIL radical is just a set of nilpotent elements. They actually form an ideal just by the binomial expansion. something like that. All right, good. So interesting ideal. Here's the key relationship between prime ideals and the nil radical. It's the first interesting fact you learn in commutative algebra. Maybe the Zorn's lemma fact was interesting to you. This is another Zorn's lemma fact. So key fact. Key first relationship between nilpotents and prime ideals. It's that the nil radical is equal to the intersection of all primes. Okay? That's the first thing. All right. We will have a geometric interpretation of this thing in the dictionary. Right? It's going to say that if a function vanishes on all the points of something called spec of the ring A, then that function is a nilpotent function. It is a function that when you raise to some power it becomes 0. Seems like a very strange thing to like try to absorb geometrically, but that's what this is saying in terms of geometric language. Okay, so how do you prove this? The proof is a Zorn lemma. One proof. Actually, I'll show you the other proof will come after we learn how to localize. That proof also secretly uses Zorn's lemma. So basically the only proof. Okay, so what you do is you construct. So one direction is easy. That the nil radical is contained in this intersection is easy. Because you take a nilpotent element, some power of it is 0, and 0 is an element of every single prime ideal. And so you use the definition of prime ideal to say that the F originally is in every prime ideal. This is easy. It's the other direction that's interesting. So the other direction. Meaning, it's one way to phrase it is using the contravariance is suppose you have an element that's not nilpotent. Then you want to show that there's a prime ideal that doesn't contain F. That's the hard part. Okay, and how do you cook up such a prime ideal? It's wonderful. You do this. You need to consider the following set. Sigma. Sigma will be the collection of ideals. Yeah, pay attention. Okay, sigma is the collection of ideals which do not contain any member of the following list of elements. All the powers of F. Ideals that don't contain any power of F. All right, we're pretending F is not nilpotent. All right, that's the collection of ideals we'll think about, and the, of course, post set, the partial order set is inclusion. I'm going to Zorn's lemma, so this is my notation from Zorn's lemma. Notice that sigma is not empty. Oh, why did I spell it? Sigma not empty. Consider the zero ideal. Right? The zero ideal is in sigma because F is not nilpotent. All right. Good. So now Zorn's lemma says sigma contains a maximal element. Oh, you have to verify Zorn's lemma. Okay, so first, verify Zorn's lemma. Hypothesis that any totally ordered chain, nested sequence of ideals in sigma has a cap that's also in sigma. Take the union again. You do the union. The union trick works in this case. Okay, so if you have a nested sequence of elements in sigma, take the union. That's going to verify the boundedness hypothesis in Zorn's lemma. Good. Next, take a maximal element. We'll call it P, because P will end up being prime. So the claim is P is prime. Okay, so how do you prove this claim? You got to verify the definition of primeness. So you take two elements outside of the prime, two elements outside of this ideal, and you want to show that the product is also outside of the ideal. So let's see if I can do this. Since X is not in the prime ideal, is not in this ideal, means that this ideal, which just means take everything in P and then also generate with X, all elements, multiples of X plus elements in P, like that. This is a strictly bigger ideal. It's strictly bigger than the ideal P. And similarly, this one. These are bigger than P. I know I'm finishing, don't worry. Then I'll read your thing. There's no turn. The axiom has been invoked. That's right. The axiom of choice. We are not finitists, okay? We want to get somewhere. All right. Okay. How can someone come up with such a collection sigma? Bocapier. I always wondered how commutative algebraists come up with anything. All right, that's kind of my goal, is to hopefully get an intuition for what will work and what will work and what in a given situation. But this one was kind of, this one is motivated by this one can be motivated by the contrapositive statement that we have here. So this is actually motivation for that sigma. In this case, there will be cases where I just don't know how to explain what. Okay, all right. So this is bigger than P, this is bigger than P. That means that some power of F has to be in this thing. Right? Some power. That's what that means. That has to mean. And so then you take the product. It's in the the ideal multiples of x times y plus stuff in P. Right? Write it out. You'll see that it has to be in this ideal. Okay? But that means that this new ideal, xy plus P, has to be bigger, strictly, than P. Because it contains a power of F. And what that's equivalent to saying xy is not in P. Okay, you can't have xy as an element in P because we have this issue. All right, so here's just file this away. It's a kind of interesting. We have constructed this Zorn's lemma situation, some kind of ideals hooked up. You take a maximal element of that thanks to Zorn's lemma verification. That thing ended up by magic, in this case, you know, that thing ended up being a prime ideal. Every commutative algebra class, the instructor will tell you about this conspiracy. That quite often, when Zorn's lemma is used in a clever way, in the context of ideals with inclusions, the sort of maximal elements that Zorn's lemma lets you talk about, quite often turn out to be prime. And I have no idea why this is such a commonly occurring thing, but every instructor has to mention this conspiracy. So I did. Okay, so there you go. That's the actual content for today. The nil radical is the intersection of all primes. All right, we'll continue basically on this exact page starting on Monday. Where? I'm not sure where we'll be. I'm looking at chat now. Let me go see what the poll is so far. Yeah, not enough people have voted. There's still a chance that the vote changes. So it's currently, yeah. So okay, but it's so 6 people have voted. Zoom. So 4 for Zoom, 2 for Twitch. Okay, so it's looking like it's gonna be Zoom, but there's 3 more people that need to vote. I'm assuming it'll go Zoom at this point, but I don't know. So wherever we'll see you next time, that's when we'll see you, either in Zoom or on Twitch. All right. Pro is voting like a Zoomer as usual. You didn't vote? Classic Zoomer. Bro, that's classic Zoomer behavior. Not voting. Okay. I'm just looking for questions. If you have questions, ask them now. Are we voting for Kappa class to be mod again? Kappa, how do you feel? Do you feel like you want to be mod one day? Has your opinion changed? Kappa? Not you, Crow. Kappa. No, but do you want to become one? I'm looking for questions. No one's asking any questions, so that's good. Meaning that's whatever it is. Oh, Haridas asks, can you change vote? Yeah, Haridas, tell me, direct message me. Oh, 1 person voted. Okay, got it. Okay, so the actual vote is 3-3. That means. That's exciting. That's exciting. So you go to the general channel class, you go to the straw poll link, it has a big yellow picture, and then you vote. And the vote is wrong. It's 3-3 right now. But I need to hear from more people in the class. Good. It's very exciting, right, Haridas? Yeah. No. Okay, if you're in the class, the vote is on the Discord channel general page. The general chat. It's a big yellow thing. It says straw poll. And it has a little link above it. And then you click that and then you vote. We're voting on whether we want to meet on Zoom or on Twitch, bro. I had a feel graduate students, they're, you know, they're serious people, bro. Serious. I suspected. Yeah, we have new emotes, Battlestorm. That's right. We've got BMP Smart, of course. I can't believe that wasn't the first emote. And then we have BMP Search. It's one of those moving ones. It's a little bit small, isn't it? But that's the size, I guess. Yeah. So we have 4 emotes now. There will be more that come. Okay. Okay, Kappa. That's Kappa. This is just classic Kappa garbage. Oh my god. All right. That means credit time. Hope everyone's having a good day. Hope you have a good weekend. Credits. All right, so who came to class? All my students came to class. That's right, Arbitrary. Yeah, that's right. No judgments, Battlestorm. These are no judging. It's just I need to know early so that we can change the class. But they're not voting. Hey, let's see. Let's look at the vote. Yes, I know many people did vote, but let's look at it now. Let me do it. Let me refresh the vote. Yeah, it's 3-3 with the correction. There's one person who needed to correct. Okay? It's 3-3 right now, so I don't know where we'll be. So class, go vote. It just means the people aren't here because I've said it many times now. Okay, great. All my students. There are former students in the chat. All right. Hope classes are going well. Hope you're staying sane, positive during this crazy time. All right. Who else? Who else is here? Usual suspects. Kappa. With the humor. Thank you. Who else was here? Yeah, Nina, or who's Nina? I don't know who Nina is. But yes, person in the Discord. I agree. I agree. Where are the voters? Did we not campaign hard enough? We didn't campaign hard enough. The voters didn't turn out. It's 3-3. We can't stop the count even. We can't even stop the count right now. Person in the Discord whose name I don't know. Oh, jeez. Okay. Okay. Actually, I don't mean all my students. I mean the voting student. Okay, there you go. Awesome. Next. Can I save it? Other person in Discord, can I really save it? I don't think so. Hey, does the Coomer surface color changing work? Is it back? I haven't tried. Okay, boring Professor Servant, also known as my brother, makes all the like this Coomer surface technology work. Set up all this screen and everything. All my mods. AC, thanks for notifying me of things. Okay, what's going on here? Oh, voting is not possible? Seems like voting is not possible for some people. Let me just, what? Okay, let me copy paste this link. This? Boca Pier. Boca Pier. You click that link? Like the link. That's interesting. Yeah, voter suppression. Voter suppression. And voter fraud, because I have to change one of the ballots. Yeah, see, was anyone supervising when I changed someone's ballot? Might be Haridas, I'm not sure. Could be. Yeah, maybe they're just all, that's what it is. They're all voting by mail. So it's gonna take a week before we figure out what the class wants. That's what it is. That's what it is. Good. Arbitrary solves it. Ancient friend. Definitely makes it in the credits. Okay, who else gets in the credits? Okay. Bro. How's it going? Turbo, welcome. Vixen, frequently seen friend. Smash Time, friend from grad school. Still my friend, but also was a friend in grad school. Okay, you want me to juggle? All right, I'll juggle. But wait, let me do the credits first. Smash Time. Hope your semester's going well. You told me you stopped. You don't have to teach this time, so okay, great. That's nice. Battlestorm. Oh, these are my old students. Work hard this semester. Not like last semester in my class. Not like that. Don't do that. Okay? Work hard this time. All right, who else? Recorder? Okay, I'll play a little recorder. I'm still waiting on I hope the class chooses something. Just choose something. Okay. There's movement. It's now 4 Zoom, 3 Twitch. 4 Zoom, 3 Twitch. It's gonna be Zoom probably. It's probably gonna be Zoom. Zoom just needs one more, and then it'll be done. So if you want to do Zoom, go and vote it. Just do that right now. Good. Okay, recorder. Where's my recorder? Oh, here it is. Pro, what do you want to hear? Pro. Oh, you have to teach more in the spring. Okay. Okay. Oh, Zoom wins? No, it's still 4-3. Remember, there's a person who switched over. Hit me with something that's not Mandalorian. There you go. That's for you. Perfect. Okay. And nailed it. That's right. Okay. And then juggle for smash time, and then we're out. And then we're out of here. In the meantime, my class of highly educated PhD students, vote. One more vote. That's all. Click it. All right, next. Okay. Here we go. Here we go. The music back on. Here we go. I'll try 5. I'll try 5 today. If I can find all 5, I'll try 5. Here we go. 5 balls. Here we go. Oh my god! This is, oh. That was like 40. That was like 40 throws. If I check the tape, Kappa, check the tape. That was 40 throws. Ah. Same vote. Oh my god. Yeah, highly educated PhD students. Just need one more person out of you. You're probably, proving Fermat's last theorem or something. Just look up and vote. Kappa, there's not enough memory in your computer to store that much juggling. I know. It was 40 throws, I'm saying. Okay, great. Let's get out of here now. I'm probably going to just do a hard exit. Thanks to everybody for showing up. Here's your credits. Thank you. Old students. Hope you have a great semester. Yes, that's right. We're doing a hard exit. Smash Time Fools. What can we do for a hard exit? Do you guys want Coomer Earthquake? Yeah, let's do a Coomer Earthquake. Yeah, Kappa. Well, let's do a Coomer Earthquake. Ready? Oh no! Oh no! Look at that! The Coomer surface is... Oh no! Oh, yeah, look at... Oh!